This meeting Zoom session is being brought to you by the fractal inverse bullseye S swirl. All right, for today, uh, we're reaching the end of the edge. We're reaching the edge of the material. We still have this 5, 6, and then after that 5, 7, the cross product, and that's the and then we fall off the edge of the topics. I might write up some other lectures based on some other sections, but then they will be extra credit because I didn't assign them at first. Anyhow, let's see. Yes, today's section is vectors in space. All right. Now let's see. Let me double check. We did yes, we did vectors before in 2 dimensions. Now it goes in 3 dimensions. So now the vectors are a direction and a length in space. It has a length, and its direction will be somewhere in 3-dimensional space, like that. You'll be given 3 components, A by B by C. A is the X component, how far it is in the X direction. B is the Y component, how far it is in the Y direction. And C is the Z component, how far it is in the Z direction. So we rewrite that as AI plus BJ plus CK. I is the unit vector in the X direction. J is the unit vector in the Y direction. And K is the unit vector in the Z direction. And like with 2D vectors, a 3D vector is a displacement, only this time in 3-dimensional space. So going to go from a point x1, y1, z1 to x2, y2, z2. The vector is the displacement between those, and its components are the differences between the points. x2 minus x1 by y2 minus y1 by z2 minus z1, like that. The length of the vector v, as written as before, with a v with a sort of double absolute value sign around it, is a square root of sum of squares of differences of components. Again, like with 2 dimensions, only we add one more term with the difference of z's. And like with 2-dimensional vectors, we can add, subtract, and multiply a vector by a constant. You add vectors by adding the component parts. The x component is a plus b, a plus d. B and y components makes they sum to b plus ey component. The z component is c plus f. And if you subtract vectors, you subtract respective components. A minus b for the x component, b minus e for the y component, c minus f for the z component. And you multiply a vector by a scalar, representing, in other words, a number representing scale. K times ABC is Ka by Kb by Kc. Again, like with 2 dimensions, only with a 3rd dimension. And like with 2 dimensions, there's a dot product. Given 2 vectors in space, their dot product will be a sum of products of components. V1 by W1 plus V2 by W2 and V3 by W3. It is also equal to the product of the lengths of the vectors but times the cosine of the angle between them. V dot W is length of V times length of W times cosine of theta. And therefore, if you divide by the lengths and taking our cosine, cosine of theta is V dot W over length of V times length of W. This dot product is like a product of numbers, only it turns vectors into numbers, so it's a little odd in that respect. It's commutative, V dot W equals W dot U dot W equals W dot U, and it's distributive over vector addition. U dot V plus W is UV plus UW. This is a vector addition, this is scalar addition. U dot U is the length of U squared, that follows from this. U dot U will be length of U cosine of 0, which equals 1. And also V dot V will be V1 squared plus V2 squared plus V3 squared, in accordance with Pythagoras. And the 0 vector, 0 by 0 by 0, dotted any vector is 0. Okay. The unit vector in the v direction is v divided by its length. Now, if you draw a vector in 3 space, you'll make an angle alpha with the x-axis, an angle beta with a y-axis, and an angle gamma with a z-axis. And the vector will be its length times cos alpha by cos beta by cos theta, cos gamma. This cosine is the unit vector in the v direction. And the alpha, beta, and gamma are cosines of, well, for alpha, it's v dot I, unit vector in the x direction, over length of v. Beta is arc cosine of v dot j over length of v. Gamma is arc cosine of v dot k over length of v. So, some examples. Find the distance between -1, 2, 3 and 0, -2, 1. Okay, well, here we do the three-dimensional Pythagoras theorem. Square root of sum of squares of differences of components. -1 minus 0 squared plus 2 minus -2 squared plus 3 minus 1 squared. -1 minus 0 squared is 1. 2 minus -2 is 4, which squared is 16. 3 minus 1 squared is 3 minus 1 is 2, which squared, oh my God. Oh my, no, it is 4. No, that's a 2. This should be a 4, and you know what? Ah. Ouch. Well, I'll have to change that one. This happens. Okay, let me make a note here. That was a definite mistake. This should be a 4, which plus 16 plus 1 is root 25, which is 5, and so that must be changed. Excuse me for a moment. I'll change that on the canvas. 3, number 17. 3 minus 1 squared is 2 squared is 4. So much must be changed. Okay, never mind that. Here we have I minus j plus k. What's its length? Well, 1, 0, 0 is I. J is 0, 1, 0. K is 0, 0, 1. If you can combine these, you get 1, -1 by 1. And its length is square root of sum of squares of components. Square root of sum of squares of 1 squared, -1 squared, 1 squared, square root of 3. Now, for these next two, 41 and 43, we're given vector v and vector w. V is 3i minus 5j plus 2k. That's 3 by -5 by 2. W is -2i plus 3j minus 2k is -2 by 3 by -2. They ask for the length of the difference and the difference of the lengths. Two very different concepts. The length of the length of the difference. Well, difference 3 minus -2, first component, second component -5 minus 3, third component 2 minus -2. This will be 5 by -8 by 4. Okay, square root of the sum of these. 5 squared is 25, -8 squared is 64, 4 squared is 16. That's square root of 105. And since I suddenly don't trust myself, I better do this by calculator. Yes, it is root 105. Fine. Length of v minus length of w. Well, you have the length of the vector v minus length of the vector w. Okay, length of this vector, 3, -5, 2 is root of 3 squared plus -5 squared plus 2 squared minus. Length of this vector here is -2, root of -2 squared plus 3 squared plus 2 squared. So this will be 9 plus 25 plus 4. Let me double check that. 9 plus 25 plus 4, root 38. Okay, -2 squared is 4. 3 squared is 9. 2 squared is 4. Yeah, root 17. So yes, root 38 minus root 17. And yes, to be sure, these are two very different numbers. There we have two vectors. What's their dot product? And what's the angle between them? V is 2 by 2 by -1. W is 1 by 2 by 3. So the dot product, we take product of sum of products of components. 2 times 1 is 2. 2 times 2 is 4. -1 times 3 is -3. 2 plus 4 minus 3 is a 3. That's the dot product. The angle between them is the inverse cosine of the dot product over the product of the lengths. Dot product is 3, we saw over here. Okay, square the length of this one is root of 2 squared plus 2 squared plus 1 squared. Length of this one is 1 squared plus 2 squared plus 3 squared. All right, and all right, 2 squared plus 2 squared plus 1 squared is a 9, so that'll be a 3. 1 squared plus 2 squared plus 3 squared is 1 plus 4 plus 9 is 14, so root 14. So the angle's arc cosine of 3 over root 9 root 14, and plug it into a calculator, you get about 74.5 degrees. So that's the angle between these two vectors. I think we'll call that